So I'd like to talk to you about several pieces of work, one of which has been done with Augusto Carballido at Caltech and JPL, and with Takeyoshi Sano at Osaka, and another piece that's been done with Takeyoshi and also with Natalia Dzurkovic at MPIA, and then some other projects that have been done along with Jim Drake at Maryland and Jim Stone here. I only have 3 things to say, but I'm going to take about half an hour. The first thing is that, at least in the minimum mass solar nebula, the dead zone is a robust feature. It's difficult to make it go away completely. But the second thing is that even though you have a dead zone, it's magnetically active and it can have magnetic stresses even if it remains laminar. And then the final thing is that because it doesn't seem to be turbulent, the dead zone has grains settling, and therefore it acts as a sink for grains in the surrounding active layers. So after Mark's talk, we were discussing basically this diagram, which is from Sano and Stone 2002. And so this is showing the saturation amplitude of the magnetic field in the MRI as a function of the Lundquist number. So the Alfvén speed in the background field divided by the resistivity in the orbital frequency. This dimensionless number, in any case, when it's when it's bigger than unity, the saturation amplitude doesn't vary terribly much with that number. But when it's smaller, the saturation amplitude falls off like a rock, and that's independent of the amplitude of the Hall term relative to the ohmic term, at least over the limited range that can be explored. So we're going to apply that criterion for magnetorotational turbulence to the minimum mass nebula.
That last curve, is that what Reynolds number was that?
Well, it's just what can be. I mean, there wasn't an explicit viscosity, so.
So you had an explicit resistivity.
That's right. Yes, that's right.
Based on the grid scale, can you estimate what the ratio was? Because you have
Oh, at the top is the same thing, but using the sound speed instead of the Alfvén speed. So probably the Reynolds number is.
Reynolds number from in Zeus with this MRI simulations that people have been doing lately is like 10,000, 20,000.
So this transition is occurring at a Prandtl number less than 1. If I take the ratio of this to the Reynolds number.
Yeah, you can do this, but it's not that big.
Protostellar misses are low Prandtl.
Yes, that's certainly true. So we're going to take the minimum mass nebula. We want to calculate the resistivity everywhere, so we need to know the electron fraction, XE here. And the electron fraction involves, as we heard from Mark, 2 sides. There's the ionization side and the recombination side. And I'm going to be as optimistic as possible, so I'm going to include the stellar X-rays with actually a scaled-up ionization rate from Igea and Glasgold's paper to the typical value that's seen in more recent Chandra surveys. And that dominates by orders of magnitude out at relatively low columns in the top 10 grams per square centimeter or so. Then cosmic rays take over deeper into the disk, but then even those are strongly attenuated at 1 AU, where you have 1700 grams per square centimeter. But then, at least if you have dust, then the dust may have radioactive elements in it. And if it has only the long-lived things like potassium-40 that can easily be delivered through the interstellar medium to the early solar nebula, then you get a relatively low floor. If you had a nearby supernova, so you had aluminum-26 delivered to the solar nebula, then maybe you could have a higher level, which could dominate over cosmic rays at the midplane. Yes, that's right. So Igea and Glasgold did a Monte Carlo radiative transfer calculation, including the scattering. And so, yes. So most of this is, especially towards the right-hand end of this curve, is all scattered X-rays, because the direct X-rays from the star are too strongly attenuated. And my chemical network is even simpler than Mark's. But we get pretty much the same answer, and other people, so Ilgner and Nelson, for instance, a couple of years ago did a very detailed calculation with thousands of reactions and found that in the presence of grains they got almost the same answer. So because the recombination on the grains is just so fast. If you have no grains, then simplifying the reaction network can lead to a slightly higher ionization fraction because you miss out on some of the recombination pathways.
How much more expensive is to complicate the reaction network when you're doing the turbulence?
So solving the reaction network at every grid cell in the MHD calculation makes it almost a factor of 10 slower. So let's go on and look at the first part of the results. So here we're looking at a cross-section through the minimum mass nebula, so extending out a little past Saturn's orbit, a couple of AU above the midplane, and we have contours as seen looking down from above of 1, 10 and 100 grams per square centimeter column. And the blue is showing where that criterion, that Elsasser or Lundquist number is, where that criterion fails. So you expect not to have magnetorotational turbulence. In the absence of dust, this dead zone is relatively small, extends out only to a little past 1 AU. If you have roughly the interstellar abundance of 1% mass fraction of micron-sized grains, then it extends out almost to the edge of this region that we're considering in the midplane. And Mark mentioned this also, you have to decrease the abundance of the grains by a huge amount to make it look like the no grain case. You have to remove 99.99% of the grains to get to this situation here, which is almost like the dead zone that you have with no dust. That seems like a tall order to strain out such a large fraction of the solid material from the solar nebula. And
Why is it so sensitive? In other words, what you're saying is that if you have the normal amount of dust grain, it's essentially overkill.
yes, that's right. That's right. I mean, the grains have a lot of a lot of surface area basically, so easily sweep up the charges.
I realized it was that thorough. You had to be that thorough in the grain removal.
Yes, yes.
Good point.
Or you grow them. You can grow them as well.
Yes, that's another option.
They start chipping each other.
So another kind of acute possibility for reducing the dead zone was suggested by Fatuzzo and Adams a couple of years ago. So they suggested that a lot of stars form in clusters. There should be a nearby massive star. It's quite likely that there could be a nearby supernova and a young supernova remnant producing a much higher flux of cosmic rays. So this shows the column density in grams per square centimeter on a log scale versus radius in the minimum mass nebula. And the dashed line shows the active column with cosmic rays at their normal rate. So it's roughly speaking, it's 10 or 20 grams per square centimeter out to the position in the nebula where that's the total column. And then after that, at larger radii, the whole thickness of the disk is active. This shows what happens if you have that nearby supernova. So the cosmic ray flux is 1,000 times greater. In close to the star, it doesn't make any difference because in the case where you have the micron-sized grains, the active layer is very close to the surface where the X-rays dominate anyway, and they have a much higher flux. At 1 AU, you get a factor of 3 or so from your 1,000-fold increase in the cosmic ray flux. If you have no grains, then the active layer extends deeper to more than 100 grams per square centimeter. But again, at 1 AU, you get only about a factor of 3 increase, which is a little disappointing after all that input of energy. So even if we can't make the dead zone go away completely, perhaps we can still make it accrete on the star somehow. So here is yet another shearing box calculation. This one differs from some of the others that we've seen in having a vertical profile for the resistivity. So we've taken the cosmic rays and X-rays, actually this one may be X-rays only, coming in through the top and bottom of the box, and we solve the reaction network to find the resistivity at each height. And in this case, we're including the well-mixed micron-sized grains. So that means that the recombination timescale is fast. The timescale to reach chemical equilibrium is very fast. and so we can safely set that resistivity profile fixed during the calculation. And the strange thing is that in the middle here, where the resistivity is very high and we have a dead zone, this is at 5 AU in the minimum mass nebula, we have a relatively uniform magnetic field with a strength of 1/10 of a Gauss or so. So next we'll look at how that can come about.
This is single fluid calculation, or do you allow for amplifold drift?
This is single fluid, so it's only an ohmic resistivity. That's the only non-ideal term.
Would be the Hall, where I think it's 5 AU.
Well, in any case, yeah, okay,
So we did go back after the fact and calculate the magnitudes of the other non-ideal terms, and the Hall term is less than ohmic at the midplane for the conditions we used, comparable to at 2 scale heights, and then at 4 scale heights ambipolar diffusion is starting to come in. So here are various quantities horizontally averaged and plotted as a function of height. So from 4 scale heights below to 4 above the midplane. And the top quantity that we're looking at here is the excess pressure due to horizontal fluctuations in the magnetic field. So in the surface layers, we have turbulence. So almost all of the pressure is due to those fluctuations. So this is normalized to the total magnetic pressure at each height. So we're near unity out here. The dashed line here marks the dead zone according to that dimensionless number criterion. And then inside the field, the pressure in the fluctuating field falls off more or less exponentially with height. And at the midplane, it's 1% or so of the background pressure. Another way to look at what's going on with the magnetic field is to look at the dissipation rate due to the ohmic resistivity, and that peaks just inside the dead zone on both sides. There is a non-zero amount all the way through the interior, but this is where it peaks. So what's happening is we have turbulence carries magnetic fields across this boundary into the dead zone, and the fluctuating part is dissipating in here. And then you can see at the bottom here the diffusion time scale in units of the orbital period. And once you're into the dead zone, this diffusion time scale is very short. It's just a couple of orbits at the midplane. So once you get in here, your remaining mean magnetic field, horizontally averaged field, will very quickly diffuse into the midplane. So the dead zone is accepting magnetic fields that are generated in the surface layers. So even though it's dead and it's not turbulent, it's still magnetized.
Would introducing a dust layer in the middle of the disk have any effect on a region of very, very high resistance?
Yes, it could. So I'll discuss in a minute. There's a criterion for when you can have radial fields generate toroidal fields and therefore a shear. If the resistivity goes too high and you violate that criterion, then you would not get the effects that we're seeing in these calculations.
The dead zone is not defined. It's not defined by where the growth is not stable, but actual measurement where there's no turbulence. Correct.
The two roughly coincide.
So there's not much bleeding of the turbulence inside of the regime where the other turbulence.
Yes, that's right. Yeah.
So your resistivity is, if I understand right, it's highly temperature sensitive in this code, isn't it? Because it depends on the electron ionization fraction, which is determined, at least the inner edge of the dead zone, thermally.
Well, all the calculations that I'm showing here are 1 AU or outside, so thermal ionization is not important. So there's still a square root temperature dependence.
It's only the square root of, okay, so the ionization fraction is fixed.
In the calculation that we just looked at, it's a fixed function of height.
Okay.
How much would those codes differ if you had infinite resistivity in this midplane? You still have some potential field.
Yes.
I mean, the horizontal correlation vector of the field in the active zone is the order of scale height, and in the mid zone at two scale heights, you're down by a factor of -2 or something. In the midplane. residual near the midplane really due to the finite value of resistivity, or is it simply essentially the Laplace's equation?
That's something that's worth looking at a little more carefully. There are, so at least for this set of parameters, there are waves on the magnetic fields. So I don't think it's quite a potential field. But yeah, there is a parameter regime where it does become potential, of course.
But if you had grains in the midplane, you no longer have this effect, is that right?
This case, or at least the case that we looked at just before, is with well-mixed grains, but at a somewhat larger radius at 5 AU, where although you're dead at the midplane, you're not completely dead.
But the amount of field that penetrates does depend on the amount of dust that you have.
Yes.
So it can't be just solution on the left of the equation.
Well, it depends on the resistivity.
Yeah, so it,
So next, let's have a look at what happens when we're not in the potential field regime and where we can have some field evolution still at the midplane. So now we're looking at the radial field, which is the dotted line. This is at the midplane and horizontally averaged. And the toroidal field, which is the solid line. And then the red line here is showing what we would expect for the toroidal field if it were to evolve just due to shear acting on the radial field. So dB wide dt is the shear rate times the radial field. And you can see that the toroidal field pretty much follows the red line over almost 150 orbits here. So what's happening is the radial field that's generated in the surface layers and then diffuses down to the midplane is being sheared out to produce the toroidal field. That's where the toroidal field is coming from, basically, at the midplane. So let's get a criterion that for when that can happen, when we can have that shear that leads to a toroidal and a radial field and therefore a stress. So roughly speaking, remember we need a length squared divided by a diffusivity. For the length, since we're looking at shear, we can use the radius. So our criterion is that the diffusion time for the magnetic field over the radius has to be longer than the orbital period for the magnetic field to couple to the shear. So, but we can write that as another sort of an Elsasser number, but with the another. So yes, yet another dimensionless number here. But it looks a lot like the other one, except with a K instead of an A. So, but it turns out that there are some geometric factors, and also we want to allow the shear to progress far enough so that we get a toroidal field that's bigger than our little seed radial field. So let's be safe and make that 10. So now we can see where that criterion is violated. And in the case with well-mixed 1% by mass micron-sized grains, the dead zone, the true dead zone goes in now to just about 1 AU, just like it is. Just like the undead zone in the case with no dust. So in all of this region in between here, we can get this effect of the radial fields diffusing down to the midplane, generating toroidal fields, and having a stress, and therefore having accretion.
What was the magnitude of the stress at the midplane?
So this is showing now the stress, but converted to a mass accretion rate per unit per scale height. So for 3 cases at 5 AU with micron-sized grains, and then at 1 AU with no grains. And so you can see that it's 1 to 2 orders of magnitude less at the midplane than it is in the active layer. So it's basically just proportional to the stress. There is yet another way to get rid of the dead zone, and that is if you have no grains, then the recombination timescale can be comparable to the timescale to mix material to the midplane. So you can have stuff ionized by X-rays in the surface layers and let it get carried down into the interior. And that happens here. We had to wait a long time, after 150 orbits or so, this effect began to kick in, and then the dead zone never goes away completely, but you get a significant time average stress in the interior, and that's the case that's shown by the red line here. And there, the midplane stress is just a few times less than the peak in the active layers.
But if you were to pull dust out of the dust layer in the midplane, you might poison
Yes,
the turbulence.
yes, that's a possibility.
The point of this, as I understand you, that instead of having to diffuse across these scale height, you now have R in that estimate for this
Yes, that's right.
disaster, whatever, the big equation. It's like big A squared over R.
Yes.
But wouldn't this toroidal field that you create diffuse in the vertical direction over scale height? Why is it R and not H?
Well, it's the system that we have is basically like a resistive plate with conducting plates above and below. And so those conducting plates prevent the field from escaping, and the fact that the interior is resistive means that whatever we get in there will spread uniformly.
So this toroidal field just uniformly spreads relatively quickly
Yes,
in the vertical direction.
that's right. That's right. So now I want to add one more level of complexity to the calculations and include settling. So now we have grains, but they're a separate fluid from the gas, and they settle at their terminal speed relative to the gas. First, let's look at settling timescales in the laminar minimum mass nebula. So for micron-sized grains in 100 orbits, which is sort of what we could hope to run the calculations to start out with, we can get down to 3.3 scale heights or something. 10 microns we can get down to 2.5, and 100 microns we can get down almost to 1 scale height within the length of time that we can run the calculations. So there's an interesting amount of settling. So it's worth doing these calculations that could take a month or two, but it's worth running them because we might see something useful.
Do you have the dynamics coupled both ways, dust, gas, and gas dust, or is it dust passive?
The dust is passive relative to the gas so far. I mean, because it's just a 1% mass fraction, and we're not expecting to see huge increases in that. So okay, here are some results from one of these calculations, and in addition to having the dust be a fluid, we also tracked some individual dust particles. And this is the case with micron-sized grains. Here are 8 particles. Each one has its track represented by a different color. And the thing to notice is that in the dead zone here, pretty much there's a little bit of stirring out here close to the edge of the dead zone, where remember we have some overshoot of the turbulence. But in the interior, pretty much all that happens is they settle to the midplane. So this is the grain trajectories projected onto the in the orbital, along the orbital direction, and here projected along the radial direction. So as the trajectories as seen from the star. So in the micron-sized case, all that happens is settling, and this shows the density history of the 8 particles. Here's the 100 micron case. The dashed lines here are showing the dead zone, which is much smaller in this case, and here it's possible for particles to mix right through. The dead zone is small enough, the overshoot regions pretty much meet at the midplane, and so it's possible for particles to go every which way all the way through in this case. So here we have the same mass fraction, but it's in 100 micron grains, so there are far fewer of them, and so the dead zone is smaller in the way that Mark described. So let's look at what happens at the midplane in those two cases. So here the black line is showing the dust to gas ratio, less unity, as a function of time in the laminar case for micron-sized grains and for 100 micron grains. And the red line is showing what happened in those two calculations with the settling. So in the micron-sized grain case, it follows the laminar line. So the midplane doesn't know about the turbulence. It doesn't know about the fact that we do have these magnetic stresses in the dead zone. The grains just keep on settling. In the 100 micron case, remember that settling time scale was not too different from 100 orbits, even down to 1 scale height. And so in that case, after 50 orbits, it looks like we're plateauing, and probably going to reach some kind of an equilibrium between the stirring and the settling. So then we would like to look at whether the settling is affecting the size of the dead zone in any way. So here are two different variables plotted, horizontally averaged and plotted versus height and time now in a calculation with 10 micron grains. And you can see, so that here's the dust to gas mass ratio. So white is a little bigger than 1%, that's where it's been concentrated slightly, and black is totally depleted of dust. And the thing to notice is that after turbulence sets in, there's intermittent settling and stirring in the surface layers. So if we were looking at the disk surface here, we'd see dust being lifted up and dropping back repeatedly. And that could affect, for instance, the temperature of grains in the surface layers illuminated by the star. And it could affect the kinds of grains, the size distribution of the grains that you're seeing. And so there are potentially many observational signatures of this kind of stirring of material in the disk surface layers. So at the top here we're looking at magnetic stress. So red is where we have relatively strong turbulence, and then the yellow regions down here are where we have this weaker mid-plane stress. The black is the edge of the dead zone according to the Alfvén speed dimensionless number. And one thing to notice is that these repeated stirrings of the dust in the surface layers are not matched by corresponding features in the dead zone. So people have speculated in the past that you could have an intermittent dead zone that grew and shrank as grains were stirred and settled, but that doesn't seem to be happening in this case.
How much of the depletion is represented by the sort of apricot color in the lower plot?
So here we're intermediate between what we got in the 1 micron and 100 micron cases. So here at the midplane we had a 20% enhancement in the dust to gas mass fraction. Here it was a fraction of a percent, and in the 10 micron case it's probably a few percent at the midplane. Maybe it gets up to almost 10% out here, something like that.
I'm sorry, the mean value average over all the mass is supposed to correspond to the white color. And you don't have a color marker.
No, well, so the initial value is 1% throughout uniform. So this orange that we get here is a 1% mass fraction, and the white is something like 10% higher than that, and the black is 0. On the other hand, there are features. So basically, what it is that controls what little features there are in the dead zone here is the magnetic field strength. So it's the Alfvén speed in our dimensionless number. There are some little features like this bump here, for instance, shows up a little bit in the size of the dead zone. So we need to know the magnetic field strength to know the dead zone size. So okay, here's a summary. Protostellar disks have an undead zone, so they have a zone where there's no turbulence, at least at the Reynolds numbers that we can look at, but nevertheless there are stresses, and that requires a kind of, it's undead in the sense that it sucks the life force out of the active layers, and that keeps it alive when it should really be dead. But we've also seen that this dead zone and the undead zone too act as sinks for the grains, and so maybe there's some hope that you can remove a substantial fraction of the grains if you wait long enough, if you wait a few settling times in the interior. And it is true that protostellar disks that may be nearing the end of their life do acquire inner holes. They're known as transitional disks, and so perhaps there's some link between those and dead zones. That's all I have.
Two questions. One is, in these simulations where people have done dust-grain flow interface mixing that produce some turbulence, I guess in those simulations, they start, obviously they must have, they have the back reaction of the dust on the gas, but I wonder what gas fractions start to become important for those numbers. And I seem to recall like equivalent of alpha is not in terms of stress, but in terms of turbulence is like 10 to the minus which is small but still finite. I guess that was one comment. Secchi, I think, is one of the authors there. And just the other question was, is it Stone and Nelson, I think, had the paper where the dead zone, the bleeding between the non-dead zone and the dead zone, and I wondered if the amount of bleeding was consistent in two simulations.
There's Fleming and Stone is one of those. So one difference is that here we have outflow boundaries on the top and bottom, and so we're allowing, even though we don't start with a net toroidal flux or a net radial flux, we can produce one by losing field of the opposite sign. And so that appears to enhance this effect in that you, in the case where you're constrained to keep those fluxes at zero, you tend to end up with equal amounts of the two opposite signs in the dead zone, and since the diffusion rate is quick there, those quickly annihilate one another. So you need to be able to produce a net flux to have this effect be as strong as it is here.
As Mark, in previous talk, emphasized, the relative importance of these three diffusivities, ohmic, Hall, and electrolytic, depend on the strength of the field. They depend on three different powers of the field. The relative ordering, therefore, of these diffusivities might be different in the nonlinear phase if the turbulent field gets to be larger than the original seed uniform field that you put in.
Yes.
Does the latter ever happen in your simulation? I mean, is the turbulent field ever stronger than the initial vertical field?
Yes, it is, and there are probably some cases where the ordering of those three changes. I mean, again, we only calculated the magnitudes of those terms after the fact,
Right.
but we did include all the geometrical factors and so on. But I'm pretty sure there are cases where if we just took our initial weak uniform vertical field and then compared that with what we get with the tangled field later on, just even the ordering of the terms would be different.
Just to state that in a slightly more exciting way, it occurred to me recently that in these protostellar contexts, there could be situations in which alpha is actually determined by these antipolar and or Hall effects because they depend on field strength, they increase with field strength. We generally don't understand how MRI saturates. It might saturate somewhat differently in this protostellar context than in more highly ionized context.
Yes.
In the regions at high Z, when you may be in a regime where the ionization fraction is high enough that you formally have an MRI, you could also find yourself in a situation where the alpine speed is just too big. There's plenty of ions around, but the density is sufficiently low that you're actually not MRI unstable. In which case you'd still have magnetic stresses. But from what you've described, I guess my question is, even if you're not turbulent in the outer layers, you'll still have this diffusion process, making the field come into the dead zone. There isn't anything about the outer layers being active which is critical to this picture, is there?
You just need a source of radial field. So it could be dragged.
It's actually, I have a hunch, or somewhat over-optimistic, in predicting MRI activity in the upper layers just by using the ionization fraction alone.
Mm-hmm.
You may have too high an alphanes, which is still an interesting problem. You still have magnetic stresses, but it may not be MRIs.
Isn't Neal simulated?
Well, but you can keep the field. I think you have a relatively low, that's a tenth of a Gauss field or something.
At the midplane,
It's a
yes.
relatively weak field, and it's purely total.
There is also a weak net vertical field that's imposed, but it's only a few milligauss.